moving into conduction velocities. Because we've already gone through the propagation or conduction of the actual action potential, but what impacts how fast it flows? What different outside factors can influence the actual action potential itself? So first off, conduction velocities are going to vary. There's several different factors that can influence and impact the speed of an action potential. Now, with that being said, these things are moving very, very quickly. Some of the highest speeds of action potentials can be pushing 200 to 300 miles per hour. So we're talking almost instantaneous from head to foot. So let's look at this one. This is going to be a dendrite. Now notice how the stimulus is right at this point, but then the actual signal and voltage kind of just fades off to nothing. That's because being a dendrite, this is a graded potential. Graded potentials cannot be re-energized or picked up and continued. They're meant to be small, localized events. But now if we look at this one, which is an axon, which means this is going to be an action potential, notice all the different voltage-gated ion channels. What this allows to occur is, as a signal starts to grade, another channel picks up and opens up and re-energizes it. And it keeps picking up over and over. So the signal, by the time it reaches the end, is still the same signal. You haven't lost strength because it keeps getting repowered, re-energized over and over. But then now let's add in some myelination. Remember, we talked about myelination as in the Schwann cells and oligodendrocytes. The purpose of myelination, at least one of them, was to help insulate, to allow for faster conduction velocity. So you can see here, the stimulus occurs. That arrow really doesn't fade very much until you get to the next node. That's because there's no escape. It's not just leaching off. The insulation keeps all the ions in. Then at the next node, you'll notice that there's a set of 3 different channels here, instead of the single channel up above it. Each of these nodes around here concentrates the voltage regulated channels into that little node. So there's a lot more ions flooding in and flooding out at that node because they can't move throughout the rest of the myelination. So what's happening here is this is called saltatory conduction. It kind of looks like you're almost jumping from node to node because nothing seems to occur in between. The signal just flies through the neuron inside of that myelination. All of those voltage-regulated sodium channels, as well as the voltage-regulated potassium channels, are all concentrated in between the myelination, where you have that node around here. So really, as the action potential moves along, it's only re-triggered or re-energized at every single node down the way. Because it doesn't have to be re-energized as fast because the myelination is keeping everything inside. It's keeping it more efficient. It's allowed to move faster. So you can kind of see like these red arrows here. It looks like it almost jumps from node to node to node. You can see the huge amounts of ions exchanging at that node. But in between the node, nothing's going on. All that's happening here is the ions are quickly moving towards the next node. So the insulation makes it more efficient. The idea of saltatory conduction. Concentrating the nodes, the myelination makes it faster to travel where there is myelination present. So some other things also impact conduction velocity. Temperature. The warmer the temperature, the higher the conduction velocity. Well, this has to do with the fact that warmer temperatures make ions a little more excited. So you increase the kinetic energy of the ions the warmer the temperature gets. Now, obviously, in the human body, you can't get too much above that 98.6-ish temperature, that 37 Celsius temperature. Because if you get too warm above that, we start to denature proteins and have a whole lot of other problems. But each degree up does help out. does increase kinetic energy. So the warmer the temperatures, the faster the conduction velocity. Diameter. The larger the diameter, the faster the conduction velocity. Because larger diameter allows less resistance to the actual flow. Think garden hose versus fire hose. The fire hose is physically larger. All that water in the center is simply just passing on through with no resistance or minimal resistance. So the larger the nerve, the more actual neurons running inside of it, the faster conduction can go. So it's helping to increase conduction speeds, the larger the diameter. Then pH. Now we can look at both acidosis and alkalosis. Now you notice there's the 7.35 and 7.45 here. That is your typical range of your pH of your blood. So if we go below 7.35, so 7.2, 7.1, 7.0 even, that's going to depress or slow down the nervous system. So that's your acidosis, becoming too acidic. But in alkalosis, if you go above the 7.45, so 7.5, 7.51, whatever, that's going to hyper-excite the nervous system. If you're thinking, well, hey, that's good, we can really get things moving. And hold on. First of all, that's going to cause problems in the blood because your pH is out of balance. But hyper-exciting means everything's happening that much faster, that much more sensitive. It's almost as if your whole system is on pins and needles. Not really where you want to be. So acidosis, too low, pH is too low, slows things down, depresses. Alkalosis, pH too high, hyperexcites or speed things up too much. So a couple things that are going to impact your conduction velocities, from the myelination to temperature to pH to diameter. There's a lot of things that can impact how your neurons are working.